All right, get ready to dive deep because today we're tackling a giant.
Oh, I love a good challenge. What do we got?
We're taking on Isaac Asimov's Guide to Science.
Now that is a hefty tome.
It is.
Yeah,
But don't worry, we've waded through it all, and we're here to share the most mind-blowing bits.
I'm ready. Where do we even start with something so comprehensive?
Right at the heart of science itself,
Okay, I'm intrigued.
curiosity. That basic human urge to understand the world around us.
Makes sense. I mean, that's what drives us to explore and discover, right?
Exactly. Asimov talks about how early humans needed practical knowledge to survive.
Oh, yeah. Like understanding weather patterns for agriculture or how to build shelter?
Exactly. But as those needs were met, curiosity evolved. It shifted from purely practical knowledge to a desire for knowledge for its own sake.
So it's like once we had the basics covered, we started asking why, just for the sake of knowing.
Precisely. And that's where the scientific method really comes into play.
Right. So we moved away from just relying on logic and deduction like the ancient Greeks did.
Asimov points out how observation and experimentation became central to the scientific process.
It's like less philosophizing from an armchair, more getting out there and testing things in the real world.
And crucially, sharing those findings with the wider scientific community.
Oh, that's huge. It's the opposite of those secretive alchemists hoarding their knowledge. This open exchange of information, Asimov argues, was vital for the advancement of science.
So where does someone like Isaac Newton fit into this picture?
Newton is a pivotal figure. I mean, he built upon the work of giants like Galileo and Kepler, taking their observations and combining them with his own brilliant insights.
Talk about standing on the shoulders of giants.
Right. He was able to use inductive reasoning to come up with his laws of motion and universal gravitation.
Which completely revolutionized our understanding of the universe, really.
No more just seeing the apple fall from the tree, we were suddenly understanding why it fell.
Okay, so we've got a grasp of the laws governing our world. But how do we even begin to apply that to the vastness of space?
Oh, that's a great question. Those early astronomers, looking up at the night sky, knew Earth revolved around the sun.
But they had no idea how far away anything actually was.
Talk about a missing piece of the puzzle. It was a huge challenge
Until what?
until the concept of parallax came along. Imagine this. Close one eye, look at something, then switch eyes.
Oh, yeah. The object seems to shift a little.
Right. Astronomers realized they could use that same principle for stars. By observing a star from different points in Earth's orbit, they could measure this tiny shift against the backdrop of other, further stars.
And the bigger the shift, the closer the star.
You got it. In 1838, Friedrich Bessel actually used this method to measure the distance to a star called 61 Cygni,
Man,
and it was trillions of kilometers away.
trillions. Okay, my mind is already blown and we're just getting started.
Right, and that's just one star.
And what about all those fuzzy patches of light in the sky? Those nebulae. Did they figure those out?
Oh, they turned out to be even more mind-blowing. Some of them were whole galaxies. Imagine that, massive collections of billions of stars, each like our own Milky Way.
And it didn't stop there, did it? I mean, they discovered galaxies clustering together, forming these superclusters.
Our tiny solar system suddenly becomes a speck of dust in this vast cosmic web of galaxies upon galaxies. It really makes you question the limits of space and time.
It's almost too much to comprehend. But let's try to bring it back down to a slightly smaller scale. How about those stars themselves? I mean, what are we actually looking at?
They're not just static points of light. Each star has a story, a life cycle of birth, growth, and sometimes a spectacular end.
Okay, so stars are like cosmic drama queens.
In a way, it all begins in these massive clouds of gas and dust called nebulae. Gravity acts like a sculptor, pulling all this material together.
And as this cloud collapses,
It heats up. Eventually, the core gets so insanely hot that nuclear fusion ignites.
oh yeah, fusion. Hydrogen atoms smashing together, creating helium, and releasing enormous amounts of energy, like a star's own personal power plant.
Perfect analogy. And the type of star determines its lifespan. Smaller stars, like our sun, being slow and steady for billions of years.
But those massive stars, they're the rock stars, burning bright and fast, consuming their fuel in just a few million years.
And some of them, well, they go out with a bang, literally.
Supernovas.
You know it. These explosions are so bright, they can outshine an entire galaxy for a brief period.
That is intense.
There was one in 1054 that Chinese and Japanese astronomers observed.
Oh, wow.
They saw it even during the day for weeks. Can you imagine that?
Absolutely incredible. It emphasizes just how dynamic and ever-changing the universe is. But for now, let's bring things a little closer to home.
Down to Earth.
Exactly. What secrets are hiding beneath our feet?
Well, understanding Earth starts with a disaster, actually.
Uh-oh, what happened?
The Lisbon earthquake of 1755, it was devastating.
I can only imagine.
It was a real wake-up call, showing just how powerful the forces within our planet can be.
I bet that shook up a lot of assumptions about the stability of the Earth itself.
It absolutely did. And it spurred scientists to develop better ways to study what was going on beneath the surface. That's how we got seismographs.
Those instruments that measure earthquake vibrations, right?
Yep, it's like taking an X-ray of the Earth's interior.
What did they find?
They discovered that our planet isn't just a solid hunk of rock.
Oh, so there's more to it than meets the eye.
Way more. They found layers. A solid inner core, a liquid outer core, a thick mantle, and finally,
The thin crust that we live on.
you got it. But even that crust isn't a single piece. That's where the theory of plate tectonics comes in.
Oh, yeah. This completely changed how we understood geology.
It explains how the Earth's crust is broken into these plates that constantly move and interact, creating mountains, volcanoes.
And explaining why the continents look like puzzle pieces that could fit together.
Yeah, precisely. The evidence is all around us, too. The Mid-Atlantic Ridge, for example, this massive underwater mountain range.
What about it?
It's where new crust forms as the plates pull apart.
So it's like a giant undersea volcano constantly birthing new land.
That's a great way to put it. It's a constant reminder that Earth is a dynamic, living planet. But we can't limit ourselves to just what we can see, right?
Right. What about all that invisible light out there? The radio waves, gamma rays, all that.
You're talking about the electromagnetic spectrum. It's amazing.
I remember learning about it in school, but it always went over my head a bit.
Think of it like this. What we see as visible light is just a tiny sliver of a vast range of radiation.
Okay.
Each type of radiation, from radio waves to gamma rays, reveals something different about the universe.
So it's like having different sets of eyes, each tuned to a different kind of light.
Exactly. And one of the most amazing tools for studying this invisible light is the radio telescope.
Oh, those massive dishes.
Those are the ones. They can detect radio waves coming from unimaginably distant objects in space.
They almost look like they're listening to whispers from the cosmos.
And in a way, they are. Radio telescopes helped us discover pulsars, for example.
What are those?
They're rapidly spinning neutron stars. Imagine the collapsed core of a dead star, incredibly dense.
So dense that a teaspoonful would weigh billions of tons.
You got it. And they emit these beams of radio waves, like cosmic lighthouses.
That is wild.
And we only discovered them because of this accidental radio window that opened up in the 1930s. Just think, a complete fluke led to a whole new field of astronomy.
It's amazing how serendipity plays such a role in science. But let's zoom back in again from the vastness of space down to the tiny world of atoms. Asimov really breaks down their structure, showing how they're not just simple spheres but have internal complexity.
He takes us through the classic model of the atom. Electrons whizzing around a nucleus of protons and neutrons like a miniature solar system.
I remember making models of those in school, with little balls and sticks.
But in reality, it's much more complicated. The atom is governed by the strange laws of quantum mechanics.
Quantum mechanics. That's the part where I feel like I need a physics degree. But let's try to break it down. Can you explain how the structure of the atom helps us understand the periodic table?
Well, think about it. The periodic table organizes elements based on their atomic number.
Right. Which is the number of protons in their nucleus?
Exactly, but it goes deeper than that. The periodic table actually reveals patterns in their chemical behavior, too.
So it's not just a random chart.
Not at all. Elements in the same vertical column have similar properties because they share the same number of electrons in their outermost shell. Those are called valence electrons.
Ah, valence electrons.
Yeah.
So their arrangement is key.
And this arrangement is dictated by the rules of quantum mechanics.
Okay, so to understand the atom fully, we need to dive into the quantum realm.
We do. Are you ready for that?
Let's take a deep breath and get ready to have our minds bent.
Okay, deep breaths, everyone. We're entering the quantum realm. Now, I know quantum mechanics can seem intimidating, all those equations and paradoxes.
It definitely has that reputation.
But Asimov does a brilliant job of breaking it down, making it surprisingly accessible.
That's good to hear. So where do we start? Back to those tiny atoms.
Even tinier. We have to start with a physicist named Max Planck.
Okay, Planck. What did he do?
Back in 1900, he had this radical idea. He proposed that energy isn't continuous.
Wait, what does that even mean? Isn't energy just Energy?
Well, we used to think of it as the smooth flowing thing, but Planck said, nope, energy comes in discrete packets, like tiny little bundles.
Bundles of energy.
Exactly. He called them quanta. It was a huge shift from classical physics. Imagine saying you can't pour any amount of water into a glass, only specific cupfuls. That's what Planck did for energy.
Okay, so energy comes in set amounts. Got it. But how does that apply to, well, anything?
Well, then Einstein comes along and uses this idea to explain the photoelectric effect.
Photoelectric effect. Vaguely rings a bell. Remind me.
It's how light can knock electrons out of metal.
Okay.
Einstein showed that light itself isn't just a wave.
It's not.
Nope. It can also act like a particle, a photon. And each photon carries a specific amount of energy, a quantum.
Hold on. So light is a wave and a particle? Now my head is spinning.
Welcome to the world of quantum mechanics. It's full of these counterintuitive ideas. This wave-particle duality, as it's called, is one of its biggest mysteries.
So are we talking about light or particles? Which is it?
That's the thing. It can be both. And it's not just light. Matter, like those electrons we talked about, can also behave as both waves and particles.
I feel like the universe is messing with me. So what determines which form it takes?
Get ready for this. The way we observe or measure them influences their behavior.
So just by looking at it, we change how it acts.
In a way, yes. The act of observation itself plays a role in shaping reality at the quantum level. It's like the universe is playing hide and seek. And this leads to another mind-blowing concept, Heisenberg's uncertainty principle.
Oh boy, another principle. Hit me with it.
It says we can never know both the position and momentum of a particle with perfect accuracy. The more precisely we know one, the less we know the other.
So it's like trying to catch a fly. The moment you think you know where it is, it zips off somewhere else.
Yeah, exactly. There's this inherent fuzziness at the quantum level. It's not a perfectly predictable clockwork universe. It's more like a cosmic jazz improvisation.
Yeah, as improvisation. I like that. But seriously, does all this quantum weirdness have any real-world implications?
Oh, absolutely. Quantum mechanics is the foundation for so many technologies we rely on. Lasers, transistors, modern electronics, none of them will be possible without our understanding of the quantum world.
Wow, so those tiny particles and their strange behavior actually power our everyday lives.
It's incredible. It's like quantum mechanics is the secret code that unlocks the true potential of the universe.
Okay, color me impressed. So we've gone from the vastness of space to the tiny world of atoms, and now we're talking about lasers and computers.
And speaking of impacts, Asimov dives into another area where our understanding of the atom has really changed the game energy.
You're talking about nuclear energy.
Exactly. Asimov takes us through the history of energy sources. Wood, coal, oil. Each step brought progress, but also new challenges. And then came the atom.
A source of power unlike anything we'd seen before. I mean, I think of Marie Curie and her work on radioactivity.
A truly pioneering figure.
But it's also a bit of a cautionary tale, right? Like opening Pandora's box, incredible potential, but also unforeseen dangers.
That's a great way to put it. Curie's research paved the way for understanding nuclear energy, but also highlighted the ethical questions that come with it.
It's a stark reminder that scientific knowledge can be used for both good and evil.
And Asimov doesn't shy away from that. He details the Manhattan Project, the race to build the atomic bomb during World War II. It's a sobering reminder of the responsibility that comes with scientific knowledge, not just for scientists, but for all of us.
Yeah, we need to make informed choices about how we develop and use these technologies. It's like holding a key that can unlock incredible potential or unleash devastating consequences.
And Asimov doesn't stop with fission, the splitting of atoms. He also discusses fusion, the process that powers the sun.
Fusion. Clean, limitless energy. I've heard about it for years, but it always seems like it's just out of reach.
It's incredibly challenging, but researchers around the world are working on it. If we could crack it, it would truly be a game changer.
Harnessing the power of a star. But even as we strive for those huge breakthroughs, Asimov brings us back to the everyday materials around us.
Oh, he gets into material science.
He does. He shows how understanding the atom has allowed us to create incredible new substances.
Like stainless steel, for instance. It's so commonplace now, but it was a revolution.
It really was. No more rusting pots and pans.
Exactly. Its resistance to corrosion changed everything, from kitchenware to construction.
And what about aluminum? I read that it used to be more valuable than gold.
It was. Extracting it from its ore was incredibly difficult.
So how did it become so common?
Scientific ingenuity. We figured out how to produce it on a large scale, making it one of the most widely used metals on the planet.
From luxury item to soda cans and airplanes. Amazing.
A true testament to the power of materials science.
And Asimov doesn't stop at metals, right?
Nope. He dives into the world of plastics, polymers, synthetic materials.
Materials that don't even occur naturally, but that we've created through clever manipulation of atoms and molecules. It's almost like alchemy.
It is, isn't it? Transforming substances, creating materials with properties that never existed before. And it's not just about mimicking nature. We're creating things with entirely new capabilities.
Like super strong composites for aircraft or biocompatible materials for medical implants.
Exactly. It's like we're learning to speak the language of matter itself and using it to create a whole new world of possibilities.
It's incredible. And all of this is tied to our understanding of the fundamental laws of physics.
Right. Absolutely. Asimov takes us on a journey through the history of physics, from Newton's laws of motion
To Einstein's theories of relativity.
oh yes, relativity.
That's where I start to feel a little lost in space-time.
It can be tricky, but Asimov breaks it down pretty well.
Let's hear it.
He starts with special relativity, which deals with the relationship between space and time.
Einstein said time is relative. But what does that even mean?
It means time isn't absolute, but influenced by things like speed and gravity. It can actually slow down or speed up depending on how fast you're moving or how strong the gravitational field is.
Wait, so time isn't a constant? It's more like a river that flows at different speeds.
Perfect analogy. And one of the most famous consequences of special relativity is EMCS.
Ah, the famous equation. Mass and energy are interchangeable, right?
Exactly. A tiny amount of mass can be converted into a huge amount of energy, like in a nuclear explosion.
Powerful stuff.
It is. But Asimov also talks about the positive applications, like how stars generate energy through nuclear fusion.
So we can thank Einstein for the stars in the sky.
In a way, yes. His work completely changed our understanding of gravity, energy, and space-time itself. And that brings us to general relativity, which tackles gravity's effects on the universe.
All right, hit me with general relativity. I'm ready to have my mind bent again.
Well, imagine a bowling ball on a trampoline. It creates a dip, and smaller objects will roll towards it. That's kind of how gravity works. It's not a force, but a curvature of space-time caused by mass and energy.
So planets aren't being pulled by the sun's gravity. They're just following the curves in space-time created by the sun's mass.
You got it. General relativity explains so much, from the bending of light around massive objects to the expansion of the universe.
So, a theory about gravity can explain how the universe itself evolves.
It's pretty amazing, isn't it? And speaking of the universe's evolution, Asimov also delves into the Big Bang Theory.
The prevailing explanation for how it all began. But how can we know what happened billions of years ago?
That's the question, right? Asimov lays out the evidence, like the cosmic microwave background radiation. It's a faint afterglow of the Big Bang that permeates the entire universe.
So we're actually seeing a remnant of the Big Bang, like a baby picture of the universe.
Exactly. And then there's the redshift of distant galaxies, which shows the universe is expanding.
And if everything's moving apart, then it must have started from a single point, right?
Makes sense, right? And by tracing this expansion back, scientists have estimated when that Big Bang must have happened.
It's incredible that we can piece together the history of the universe like that.
But there are still mysteries. Asimov talks about dark matter and dark energy.
Dark matter, dark energy. Those sound a bit spooky.
They do, right. We can't directly observe them, but they make up the vast majority of the universe's mass and energy. We know they're there because of their effects on visible matter and the expansion of the universe.
So even as we unravel some of the universe's secrets, there's still so much more to discover.
And that's the beauty of science. It's a never-ending journey of exploration, driven by curiosity and the desire to understand.
Makes you really appreciate the vastness and complexity of it all and our place within it.
It really makes you realize how much we don't know and how much there still is to discover.
That's the exciting part. But before we get too lost in the vastness of space, Asimov brings us back down to Earth, literally.
Down to solid ground.
Exactly. He takes us on a journey through Earth's history, exploring how our planet has changed over millions of years.
Oh, he gets into geology. I love how he connects everything.
Me too. Remember plate tectonics? We talked about it earlier. Asimov explains how these massive plates constantly move and reshape the Earth's surface.
It's incredible to think that the ground we walk on isn't static, that it's in constant motion, creating mountains and valleys and everything in between.
Like a giant slow-motion dance. And remember, continental drift. The idea that the continents were once all connected in a supercontinent called Pangaea.
Oh, yeah. I remember learning about that in school. It's fascinating to think about how those continents have slowly drifted apart over millions of years, shaping the world we know today.
Asimov describes how these plates move apart, collide, and slide past each other, creating all sorts of geological features. Volcanoes, earthquakes, those deep ocean trenches. It's all connected.
And it's all happening right now beneath our feet. It's almost unnerving when you think about it, but also kind of awesome.
Right. It's a reminder that Earth is a dynamic, living planet. And then, of course, there's the story of life itself. Asimov takes us through the incredible journey of evolution, from those first single-celled organisms to the amazing diversity of plants and animals we see today.
It's a story that never gets old. And Asimov does a fantastic job of explaining Darwin's theory of natural selection, showing how life has adapted and changed over billions of years, driven by the forces of the environment.
It's like nature's grand experiment, constantly testing out new variations, and the ones that work best survive and pass on their traits.
And the fossil record provides this amazing chronicle of that experiment, showing a clear progression of life forms from simple to complex.
It's humbling to think about the vastness of time and the incredible journey that life has taken on this planet.
It really puts things in perspective. We're just a small part of this grand evolutionary story.
But it's a story that's still being written. Asimov doesn't just focus on the past. He looks ahead to the future of science, exploring the challenges and opportunities that lie before us.
Oh, yeah, he talks about those cutting-edge fields that are rapidly changing our world. Biotechnology, nanotechnology, artificial intelligence. It's mind-blowing.
It feels like we're on the cusp of a technological revolution that could change everything. It's exciting, but also a little bit daunting, to be honest.
Absolutely. Asimov recognizes both the potential and the risks of these advancements. He reminds us that we have a responsibility to use science wisely for the benefit of humanity and to carefully consider the ethical implications of these new technologies.
It's like we're holding this incredibly powerful tool, and it's up to us to decide how we're going to use it.
It's a decision that requires careful thought, open discussion, and a commitment to using knowledge for good.
So as we wrap up this deep dive into Asimov's Guide to Science, what's the key message you hope our listeners take away?
I think it's the importance of staying curious. Asimov's own boundless curiosity is what makes this book so engaging, and it's a reminder that the pursuit of knowledge should be a lifelong endeavor.
It's that spark of curiosity that drives us to explore, to ask questions, to seek answers, and ultimately to understand our place in this vast and complex universe.
Science is not just a collection of facts. It's a way of thinking, a way of approaching the world with a sense of wonder and a desire to learn.
And that's something we can all do, no matter our background or expertise.
So keep exploring, keep asking questions, and never lose that sense of wonder.
And until next time, stay curious.